It is 10, so we'll begin. In case you haven't seen my message yet, the test should be graded. You should see your score out of 100. The column's probably called like test 3 score or test 3 grade. I will make test 3 itself available later today, so you can actually see what you got wrong and what you answered and what the correct answer was. And then if you have any questions on how I graded something, please let me know at that point. And I'll also update the dropped test, which test is the lowest and it's being dropped. I'll also update that later today as well. But moving on, as you can see, I have the April 2nd PowerPoint up, even though I know it's not the 2nd. So we're going to finish the April 2nd PowerPoint. That shouldn't take too long. And then we'll jump into the April 7th PowerPoint. That should be online under the Test 4 folder. So let's get right into it. And we've been talking about light as our latest topic. And we've kind of talked about light away from chemistry itself, just the idea of light and the energy of light and the frequency of light. So let's connect it back to chemistry. So certain atoms will release light when they're excited, and they have to be in the gas form. You probably are most aware of this when it comes to like neon lights. You know, if you think of Las Vegas and all those neon lights, all that's happening there is that they have gas and they're exciting gas with electricity, and that gas is giving off that light. Here in this image, we have a hydrogen gas being excited by electricity, and when it gives off light, the light looks to us to be one color. However, if you take that light and you focus it through a slit, and then you separate it using a prism, you can see this light's actually made out of different wavelengths of light. And these wavelengths of light are discrete, in that, you know, if you look at hydrogen, you will get these exact wavelengths and only these wavelengths. So, you know, if you take like white light with a prism, you'll get a rainbow. You'll get all the colors of light. Molecules, though, they will only emit light of certain colors, of certain wavelengths. And each gas molecule will have a different set of wavelengths that they will emit. And what's interesting is that when we look at emission and absorption, they are the same wavelengths. What I mean by that is at the top, these brighter colored lines, they are showing you what wavelengths of light gaseous mercury will emit. So if you have mercury in the gas form and you hit it with electricity, these bright colored lines are what is given off by mercury. And if you take that same mercury and instead of exciting it, you shoot white light at it. So let's say you have your sample of mercury here and you have a light bulb. Whoa. Yeah, that's not a bad light bulb. You shine light at it and you let it, that's not mercury. That's not the symbol for mercury. You let it go through mercury, and then you have a machine here to see, okay, what wavelength of light is coming through. And when you do that, you'll notice that the wavelengths that are absorbed by mercury, that is what is not on your detector, are the very same wavelengths that mercury emits. So what that is saying is that an element will emit a certain wavelength of light, certain wavelengths of light, and they will absorb those same same wavelengths of light, right? That's what those plots are showing. There on the bottom left, what I'm showing there is different metals, and you put a fire to them, and they'll give off different wavelengths of light. So it's the same idea as the gas. And that's one way to determine if you have like an unknown metal, what metal is it? You light it on fire and you see what color the flame becomes, because it's releasing that wavelength of light because it's getting excited. So all elements do this. When they get excited, they release certain wavelengths of light. And to describe this phenomenon for hydrogen, Rydberg here created an equation. He was able to determine for hydrogen what wavelengths of light should be absorbed and emitted, and he related that to energy levels, right? So he said that, hydrogen has certain energy levels it can be in, and they're just non-zero numbers that are positive. So you can be at the first energy level, the second energy level, the third energy level, all the way to infinity. So your energy levels can be 1 to infinity, right? And what Rydberg said is that when you're going to different different energy levels. So let's say that you just begin in the first energy level and you go to the fourth one, that corresponds to a certain wavelength of light. So if you're going to the first to the fourth, what that usually means is that you have to absorb energy, absorb a certain wavelength of light. So when you go on higher energy, you absorb light to do that. It's almost like climbing stairs, right? You have to put energy in to climb stairs. And if you start at the fourth energy level and you drop down to the first one, that's when you're giving off light, right? So if you go down in energy, you release light. If you go up in energy, you absorb light. I'm missing an S there. And the S doesn't go there. Absorb. I do not know how to spell. So this equation tells us what wavelengths of light we'll be looking for, either to absorb or to release, based on what energy levels we have. For M is the energy level we start in, N is the energy level we end in, and we have a constant, so we can relate this to wavelength, and that's called Rydberg's constant. However, Rydberg couldn't explain why this happens. He could just predict what wavelengths of light would be possible for hydrogen. So let's use the Rydberg equation here, right? So I want you to calculate what light will be emitted when we have a transition for an electron. And tell me what type of light it is: infrared, visible, ultraviolet, etc., etc. If going from the first to the second energy level, or to the first to the third. And I just noticed a typo when I was reading this. Since we're starting at the first and going up, we will always absorb light. So see if you can figure out what wavelength of light we're dealing with here, and tell me on the electromagnetic spectrum down here where it falls. So I'm going to give people a couple minutes to get their hands on the Rydberg equation, and then I'll be back. If you have questions, please let me know. All right, so let's take a look at the Rydberg equation here. So let's go with A. I'm going from the first energy level to the second energy level. Question here, why is there a m-1 by the R constant? Is that the unit? Yes, that's inverse meters, and I'll show you what that means when we're doing the equation. It's important that it is inverse meters. Another way to write this is the unit is 1/meters. That's what the -1 means. All right, so let's calculate the wavelength of light we need to go from the first to the second energy level. So 1/lambda, remember lambda is wavelength, equals Rydberg's constant, 1.098 times 10 to the 7th inverse meters, multiplied by my initial energy level, so 1 divided by m squared. M is 1, so 1 divided by 1 squared, minus 1 divided by n squared, which is 2, so 1 divided by 4. Right? So when we do that, we see that 1/wavelength is equal to 8235000 1/meters. However, I don't want 1/meters. I want a unit of meters. Also, this is 1/wavelength, right? So in case you haven't come across this before, right? The way to flip this 1/wavelength and just make it wavelength, you take each side of the equation and you do 1 divided by whatever's on that side of the equation. So what I mean by that is to flip this equation to have wavelength be equal, you do wavelength is equal to 1 divided by 8235000. And when you do that, this 1/meters becomes meters. All I did there mathematically is that any number, any whole number is actually just divided by 1. And so what I said is, okay, I'm going to flip this. I'm just going to take this lambda and put that at the top. And I'm going to do that 1 and put it on the bottom. And if you do something to one side of the equation, you have to do it to the other side of the equation. So I'm going to take this 1 and put it at the top. And then I'm going to take this 8235000 and put it on my denominator. That's how I get to here. And my units does the same thing. It's 1/meters. So you do that same flip and it becomes meters. And so putting that into your calculator, you see the wavelength is equal to 1.214 times 10 to the -7 meters. When we look on the electromagnetic spectra, here's times 10 to the -7. So we're like we're just past that. We'll draw a straight line. That is the ultraviolet spectra. So for the hydrogen atom, if I want to go from the first energy level to the second energy level, I have to shoot my hydrogen atoms with UV light that is exactly this wavelength. That's what this equation says. That's what this means. So if I was to look at the absorption spectra for hydrogen, I would expect a dark band right here in the UV range because hydrogen will constantly absorb that light, right? And making that first to second energy level transition. Questions about that idea? While I write out the other one. How did I get 1.214 times 10 to the 7th? It's 1 divided by 8235000, right? So you do the math here, and you'll get 1 over lambda equals this big number. And then to just get lambda itself, you take this big number and you do 1 divided by it, because I'm flipping both sides of the equation. Because I don't care about 1 over lambda. I don't care about 1 over wavelength. I care about wavelength. So I just need to invert. Another way to write the Rydberg equation, right, if that's confusing to you, it's just this. That's the same thing. So you can solve it like that if you'd like. Okay, so doing the second one, all that's different is this this second variable. So instead of 2 squared, it's going to become 3 squared. So 1 over lambda equals 976,000,000. Then you do this whole inverse thing here, and 1 to 3 is just 1.020 times 10 to the minus 7 meters. Again, UV. So that's the Rydberg equation. That's how you use it. That's how you solve for wavelength in meters. And then we can go back to our electromagnetic spectrum and see where it falls. Again, this equation is really only useful for the hydrogen atom, though. So you can only use this for hydrogen. We can't use this to predict like any other element. But this is how it started, right? This was the very first time that we could predict, what wavelengths of light will an atom absorb and what wavelengths of light will an atom emit. And again, we have no idea why it is when this equation came out. We could just use it to predict, though. So any questions about that idea? All right. So some decades passed after the Rydberg equation. And then in the earliest 20th century came Bohr. And Bohr had a model of the atom. Bohr's model of the atom was this. You have a nucleus in the center. And around that, you have like these orbits of electrons. So he thought that they just travel in a circle. He thought that the atom was like the solar system where you have like the sun in the middle and then planets rotate around that, which is wrong. This is not what an atom looks like. But we can use his idea to understand why atoms absorb and emit light and why they only do it at certain wavelengths, right? And that's what's being shown here in the center. So we can think of the orbits of electrons as energy levels, right? So the orbit that is closest to the nucleus has an energy level of 1. The second farthest away has an energy level of 2, 3, 4, 5, all the way to infinity, right? And what he proposed was that for an electron to travel to different different energy levels, you needed energy to do that. Well, light is energy. If you remember our equation, E equals the Planck's constant times frequency. right? So light is energy. So what he said is that the reason why atoms absorb light is because their electrons are jumping to different energy levels. The reason why they give off light is because their electrons are relaxing and releasing that energy back. So let's take a look at this using this image. So let's say that we have an electron starting at energy level 2 here. Right? So here's my electron. And let's say we will take our atom here and we'll shoot it with light. We'll shoot it with red light at 656 nanometers. That electron will absorb that energy and use it to jump to the third level, right? Which is shown here. And then it will hang out in the third energy level, and eventually it will spontaneously fall back to the second energy level. When it does that, it releases the same energy of light back. So what this tells us is that the gaps between energy levels are a fixed value, right? The gap between energy level 2 and 3 for this atom always requires red light at a wavelength of 656 nanometers. That's why when we look at certain atoms, they only give off certain wavelengths of light. They only absorb certain wavelengths of light. It's because their energy levels are a certain gap apart. And once we understand this concept, we can start thinking about energy levels and some things that go along with this is, like I said, when you're going to a higher energy level, you absorb light. When you fall down to a lower energy level, you release light. The bigger the jump you make, the more energy you have to absorb, right? So here's UV light, here's IR. UV light is the light that gives you sunburn. It has a lot of energy. IR light, infrared light, is heat, right? It's the heat that comes off your body is IR light. That has much lower energy. So purple light actually has more energy than red light. And from this image, we can see that the bigger the gap we want to cross, the more energy we need, which makes sense, right? If you're jumping between a gap that's energy level of 2 to 5, you need more energy than you would if you're jumping a gap that's 2 to 4 or 2 to 3. So that's something else, right? The bigger the gap you want to jump, the more energy you need, the higher energy of light you need to make that happen. So that's what the Bohr model is, and that's how we can start to understand these emissions and absorptions of light. It has to do with electrons moving to different energy levels. All right. So before we move on to actual problems, is there any questions about like that theory or anything I said there? All right. So here's just a simple question. See if we just understand this concept before we get into more complex stuff in our next PowerPoint. Just tell me for A, B, and C, are we talking about an absorption of energy, or are we talking about an emission of energy for these different wavelengths? So just take a minute and decide if we're looking at light being given off or light being absorbed. So work on that, and I'll be back in just a minute. All right. So no real math here. It's just, do you understand the processes of energy levels? And basically, if you start at a high energy level and you fall, you release energy. So that's an emission. And then if I start at a low energy level and I go to a higher energy level, I need to absorb energy. So that's an absorption. So 4 to 3 would be an emission then. All right, any questions at all? And feel free to type those out while I switch PowerPoints here. All right. If not, let's move on to the 7th. And we're going to get into something that's really complicated. And I know you're probably saying to yourself, well, it's been complicated all semester. So what's new about this? Well, what's new is that we're going to get into quantum mechanics. Quantum mechanics, and we're just going to like barely touch the surface. But quantum mechanics is mechanics that are used to describe extremely small things like electrons. Most of your life, you have been dealing with Newton mechanics. That is, everything has an opposite but equal like reaction. Like if you push against a wall, the wall will push against you with the same force. If I throw this pen, right, it will arc based on physics. Quantum mechanics is different in that things can just like teleport. So electrons can be in one position, like in one space. And then that next time you look at it, it just teleported to another space. Like you can't watch it move. It's just there, then it's somewhere else. That's called quantum tunneling. So it can do things that normal objects can't. And also with quantum mechanics, things only happen like a percentage of the time, right? We can predict where an electron will be a certain percentage of the time. It's not going to be there always. That gives some really weird thought experiments. So with quantum mechanics, one interesting thought experiment is, let's say that you punch a wall, right? You don't punch it hard, but you're just like hitting a wall with your hand. Quantum mechanics says that one of those times when you go to hit the wall, all of the atoms will spontaneously move away and you'll go right through the wall with like no resistance. The atoms will just part and there'll be empty space and your hand will just go through that space. Now, the probability of that happening would probably take you, the lifetime of the universe to see that event happen once. But quantum mechanics says that eventually that would happen. This is where the famous Einstein quote comes from, where he said that God doesn't play dice or something like that, where quantum mechanics was really presented in like the 1940s, 1950s. And Einstein was, at the end of his career there, and he did not believe that quantum mechanics existed. He said, this is crazy. No way that electrons follow this new wild physics, right? It can't happen. He was probably wrong, but he was very much against quantum mechanics. But since we think quantum mechanics is actually correct at predicting how electrons behave, we're going to jump into quantum mechanics here. And to begin with, we have to learn about quantum numbers, all right? Now, what quantum numbers are, they're a set of numbers that we use to define where an electron is around a nucleus. That's all it is. So they're like a set of coordinates to say, okay, we know probably where the electron is. However, since we're dealing with quantum mechanics, it's not like XYZ coordinates, where what you might think of like, okay, I give it an X, I give it a Y, I give it a Z, I can pinpoint where it is in space. We can't do that. Instead, we have to make up new numbers. And the first quantum number we're going to look at is called the principal quantum number, and we give it the unit n. So n is our first variable. And n is just what energy level is our electron currently at. This is the same thing as the Bohr model we just looked at the last slide, in that the energy level you have to be at has to be 1 or greater than 1, and they have to be integers. So you can be at an energy level of 1, 2, 3, 4, all the way to infinity. Now, when we look at the energies of this, the bigger the value of n, the more positive energy, or the more positive the energy becomes. So instead of more energy, the more positive the energy becomes. Overall, all of the energies are always presented as negative, right? The closer you are to 1, the more negative you are, which is good. Negative energies are a good thing. That means you're relaxed. As you move further and further and further away from the nucleus, that's what these energy levels are, your energy becomes closer and closer to 0, until you're so far away, your energy is 0. When your energy is 0, that means as an electron, you are no longer bound in the orbit of the nucleus. You just fly off into space. It's like a comet almost, right? So a comet, for the most part, will just go around the sun. But what if that comet broke away from the sun's gravity and just flew off? That's what I'm talking about here when the energy level becomes 0. And we can calculate what is the actual energy value of an electron at any value of n, which is this equation. So the energy value at some level of n, so what energy are you at a level of n, equals negative 2.18 times 10 to the minus 18th joules, there's our friend joules, multiplied by 1 over what energy level you're at squared. So you can see at the first energy level, we're at negative 2.18 times 10 to the minus 18th, because 1 divided by 1 squared is 1. As you move further up, so the second energy level, you just put a 2 there. Third energy level, you put a 3 there. Fourth energy level, you put a 4 there, so on and so forth. So that is our first quantum number, just saying what energy level is our nucleus at, and that has the value of n, or not our nucleus, our electron. All right, so that was n. The second quantum number is L. You put 3, 4 in place of n, depending on what energy level you're at. What I meant by that is if you're in the third energy level, you put 3 there. If you're in the fourth energy level, you put 4 there. If you're in the fifth energy level, you put 5 there. If you're in the 1000th energy level, you put 1000 there. That's what I was trying to show there. So our second quantum number is called angular momentum, and it gets the variable L. This will tell us where the atom is, or sorry, where the electron is around the nucleus. And there are 4 common values of L. So let's just look at these first, the 4 values of L and what they mean, and then let's talk about how we can, what rules govern giving these quantum numbers to electrons. So the 4 values of L are 0, 1, 2, or 3. If you're an electron and you're given the quantum number of L, what that means is that you're going to be found in a sphere around the nucleus. So that's what this image is showing. You're going to be somewhere in this 3D sphere around the nucleus. If you are given the quantum number of 0 for L, we also call this an s orbital for sphere, right? If you have a quantum number L that's equal to 1, you're going to be in this balloon shape or this figure 8 shape around the nucleus. You're going to be found somewhere in this cloud. And we call that the p orbital. If L is 2, you're going to be in this clover shape. You're going to be found somewhere in here if you're an electron with a value of L of 2. That's the d orbital. If your L equals 3, you're going to be in some weird shape that I can't really describe. So like Wikipedia says, it looks like 8 balloons tied in knots. Sure. You're going to just be found in one of these spheres somewhere around the nucleus. We call this the f orbital. So there are 4 different orbitals you could be in: S, P, D, or F, which corresponds to L values of 0, 1, 2, and 3. All right, so how do we determine what L value an electron can have? And it's based on the principal quantum number n, right? So let's look at an electron. So here's an electron. I'm going to call this electron A. And let's say I told you electron A had a principal quantum number of 1. It was at the first energy level. And I asked you, what would be its possible angular momentum quantum numbers? Or where would I find it around the nucleus? What shape would I be looking for where it could be? That's where this comes into play. This says that values of L range from 0 to n minus 1. So this says that if n is equal to 1, the possible values of L are 0 between 1 minus 1, which is 0. So if you're in the first energy level, the only value of L you could have is 0, which is called the s orbital, which means in the first energy level, an electron is going to be found in this sphere. We don't know where it's going to be found in here. We just know it's going to be in there somewhere. Let's look at a different electron, electron B. I said electron B is in the second energy level, has a principal quantum number of 2. Then I ask you the same question. What value of L could it have? So we have to do the same math. L ranges from 0 to n minus 1. Here n is 2, so it ranges from 0 to 2 minus 1, which is 1. So it can be 0 to 1. It has to be a integer. So this means that if you're at the second energy level, your values of L could be 0 or it could be 1. All right. When determining these quantum numbers. Remember, these are coordinates, more or less. So you can be, if you're at the second energy level, you could be either 0 or you could be 1. You can't be both. You have to be one of those numbers, which means at the second energy level, you could be found in this sphere, or you could be found in this figure 8, right? Just knowing the principal quantum number doesn't tell you if you're in the s orbital or the p orbital. It just tells you that it's possible to be in those orbitals, right? And we can take this exercise even further. If we go to electron C, whoops, that's not a C, that's a C. And we say, well, here, electron C has an energy level of 3, which means L has a possible range of 0 to 2. Remember that 2 is coming from n minus 1. 3 minus 1 is 2. So if you're in the third energy level, you could have a angular momentum coordinate of 0, or you could have an angular momentum quantum number of 1, or it could be a 2. It can be either one of these if you're in the third energy level. So you could have an s orbital or a p orbital or a d orbital. Again, all that means is what geometry are you likely to be found at around the nucleus? Are you going to be in a sphere? Are you going to be in a figure 8? Or are you going to be found in this clover leaf? That's all L tells you, and that's how we decide L. All right. Questions about those ideas? Right. And let's add a third quantum number. So this is our third coordinate. It's called MSubL. This just tells us the orientation of L. So if it goes up to orbital 3, so I'm guessing by orbital 3 you mean energy level of 3. It could be either 0, 1, 2, or 3, not just 3. It can't be 3, right? If you have an n of 3, L goes from 0 to n minus 1, right? If n is 3, it goes from 0 to 2. So it can be 0, 1, or 2. If you want to be in the third angular momentum number, right, you need an energy level of at least 4. Because if your energy level is 4, your L values, which are 0 to n minus 1, would be 0 to 4 minus 1, which is 0 to 3. So at the fourth energy level, you could either have an L value of 0, or 1, or 2, or 3. You can be either one of those. We don't know which one just from this number, though. Yep. So then the next one number is called MSubL. This tells you orientation of your orbital. So this just tells you what direction your orbital is pointing. So let's go to the p orbital, which is L equals 1. And you have 3 directions, right? Your figure 8 could be on the x-axis. Your figure 8 could be on the y-axis. Or your figure 8 could be on the z-axis. So just imagine like a 3D plane, if you can. And it's either that, I guess, let me just stop sharing. So for these different orbitals, So imagine, so my pen being in this direction, that's one value of L. My pen being in this direction is another value of L. My pen being in this direction is another value of actually MSubL, not L. So that's what I mean by like orientation. Which direction is my pen facing? So different orbitals have different directions they can be in. That directionality we call MSubL. And values of MSubL range from minus L to plus L plus 0. Right? So what does this actually mean? So let's say we had electron D now. And I told you electron D had the energy level of 2. And I also said, we know its L value, and the L value is 1. And I asked you, what direction is this L value facing? Or what is the value of MSubL? And the possible values of MSubL is given here. It's minus L to positive L. Let me do cursive here so it doesn't look like 1. Minus L to positive L, including 0. So for this, your MSubL could be -1, it could be 0, or it could be +1, right? It can't be all three. It can only be one of these because it's telling you what direction is your p orbital facing. So is your electron going to be found somewhere in here on the x-axis, or is it going to be somewhere around here on the y-axis, or is it going to be somewhere around here on the z-axis? Let's look at electron E that had an energy level of 4, right? And let's say I told you, well, the L value for this electron is 3. What's MSubL, right? So it's the same thing. MSubL ranges from minus L, so -3, to positive L, which is +3, including 0. So your MSubL could be -3, or -2, or -1, or 0, or 1, or 2, or 3. Each one of these numbers just means a different direction your L orbital is pointing, right? Just like that pen example I was telling you. But it gets a lot more complicated once you get into these higher orbitals. So we're not going to worry about like what those look like. Just know that's what MSubL means. Like, what direction is your L orbital facing, and what values we assign to it. So you'll never know the exact position of an electron, just what it could be. Yeah, that's the problem with electrons. Electrons have like two things that define it. It has either position, it has position, and it has velocity. Those are the two things you need to define like where an electron is at any given time. And the funny thing about electrons is that if you find out what its position is, you automatically change its velocity. So now you don't know where it is. If you figure out its velocity, it automatically changes its position. So you don't know where it is. So actually measuring an electron changes the properties of that electron. It's weird. Also with electrons, you can link them together, like where they will react to each other. And then you could separate them by the distance of the universe. So they're on opposite ends of the universe. And if you change one electron, the other electron will know that that one's been changed, even though they're across the universe, and change itself. Electrons are really weird because they're so small. They're really hard to understand. But yes, it is interesting, but it hurts my brain. Just one more thing to talk about for this. Let's look at the s orbital. L is 0. So how many values of MSubL are there? There's 1. right? Because it ranges from minus L to plus L, well, minus 0 to plus 0, which makes sense. The s orbital, if you remember, looks like a giant sphere. A sphere only has one direction, right? It's a sphere. If I turn a sphere, it's still a sphere. It looks exactly the same. So that's why there's no position for the s orbital, because the s orbital is just a giant sphere. While the other orbitals do have shape to them, that's not a perfect sphere, so they do have directionality. That's what MSubL is. And that is your crash course in quantum mechanics. We'll continue this on Friday, though. Yeah, so we'll probably jump right into questions. Let me see here. Yeah, so we'll get right into questions on Friday. So that's a good way to remember what we just talked about. If you have any questions about this stuff or you want to learn more about quantum mechanics, let me know. I'll be happy to share the little I do know of that. Otherwise, I'll put a homework up due next week, and I will see people later. Thank you for stopping by. Thank you for watching on YouTube. Hope you have a good rest of your day.